For example 2, we're going to find all the reactions and member forces, and we're actually going to do the math out for this one, since it's going to be a little different. Check determinacy. We are assuming it's not connected. It could be that would be fine. Again, the math would eventually work out the same in terms of determinacy. So our number of joints is going to be 4, and our number of external reactions 3, plus our members 6. So I've got R compared to 2n. 9 is greater than 8. Once again, I am 1 degree indeterminate, but because my reactions are equal to 3, this is internally indeterminate. Which means my second step, I can find the reactions using equilibrium. So I can sum my forces in X. Let's call this AX, AY, BY. AX is 5 kips to the left. So my moment's about A. Got BY times 20 feet minus 5 kips times 15 feet. BY is 3.75 kips upward. Sum my forces in Y. AY has to be 3.75 kips downward. So I have found my reactions. Place those. So I have them 3.75 kips. 5 kips. Okay. So now what I want to do, I've found all my reactions. Check. I need my member forces. So before I jump to method of joints or sections, I know it's indeterminate. I am going to need to use force method to find the internal forces. Do that by removing a redundant member. So we want to make sure our structure stays stable. So when you're taking a member out for internally indeterminate, you want to make sure you keep triangles. We don't want to make any squares or rectangles. That is not stable with a truss. So we want to make sure, maintain triangles. Easiest one to take off. You'll notice in the introduction, it was internally determinate. We had cross bracing like this. That's incredibly common. So my suggestion to you is take out one of your braces. That's going to be the easiest way to maintain stability and remove something redundant. I'm going to label this A, B, C, and D. So I am going to set force AC equal to 0. So what that's going to look like for my primary, I'm going to draw the same exact truss. I'm going to keep my 5 kip load on it. I'm going to keep this diagonal intact, and this one I am going to cut so that the force can't transfer through it. This is a 0 force member. Force AC is 0. And when it's not cut, I can transfer force and that member moves continuously. But when it gets cut, a gap can form. And we're going to call that gap delta 1. So between the two pieces of the member that got cut, they can move. So I've literally made a cut like this. And I've super exaggerated that because of the 5 kips, it's going to move to the right, pulling that top piece of the cut further away from the bottom piece, leaving this gap of delta 1. So because I've taken something off, I need to put it back on. So I'm going to apply a unit load to the cut member. Remember, this is our primary structure, just like before. This will be our redundant applied. So what's this one going to look like? I'm going to draw the same exact thing, except now this member, I'm going to put the unit force here. If I apply a unit force here, I have to have equal and opposite so that my member force AC is now equal to 1. I've put it in tension. You could put it in compression if you wanted to, but I've drawn the arrows away from the member. So now I have these two pieces that have been separated, and I've put a load in there that is now pulling them back together, so that could close the gap or even overlap the gap. That is my F11. But what I know is that in my real structure, there is no actual gap in that member, right? That member is one continuous piece. So here at the cut, the deflection there is actually 0. In my primary structure, it's delta 1. In my redundant applied, it is F11, and this whole structure needs to be multiplied by force AC. So I'm going to see delta 1 plus force AC F11. The only reason I switched to numbers instead of subscripts, I don't want to write delta AC and FAC AC. That gets messy very fast. So that's why I switched to the numbers. But it looks very similar to what we did for externally indeterminate trusses and our beams. Alright, so we are going to enforce that compatibility. We need to calculate delta 1 and F11. And again, the only method we have is virtual work. So I'm going to do virtual work. I'm going to do it on the next page because I have more room. When I'm doing delta 1, my primary is the real structure because that's where I see delta 1. Just like we saw with the externally indeterminate, our primary is our real structure, right, for delta 1. This. We can just draw that member as is. We know it's a 0 force member because we've cut it. Pin and our roller. This looks just like our primary structure for delta 1. And the good news is our reactions are the same because externally we haven't changed anything. We still have the 5 kip load. We didn't change our reaction supports, so this is still 3.75 kips. 3.75 kips and 5 kips. The only thing we changed was internally that member is a 0 force member. And we can draw the virtual structure. Virtual structure looks exactly the same, except we don't have that 5 kip load, and instead this member has a unit load on it because we were trying to calculate the displacement at delta 1, just the displacement in that member. Here NAC is 0, here NAC is 1. Now we just have to find the rest of the member forces. So first step, I'm going to look at my real one, and I'm going to look for other 0 force members. So if I'm having trouble visualizing this, I can take off my 0 force member. It's as if it isn't there. It is there for stability purposes, but for calculating other member forces, I can do that. Here, this is 0 force, looking at joint C case 2. This one has to be positive 5 because they're collinear. Here we have a nice cross shape, so this must be 3.75 and this one must be 5, all getting pulled in tension. So the only member we're missing is that diagonal BD, so I can look at joint B or D. So I've got 3.75, 5, and NBD. Doesn't matter, some force is in X or Y. I've got 5 plus NBD, and this triangle, 20 feet, 5 feet, so this is 3, 4, this is a 5, 3, 4, 5 triangle, so this is 25 feet on the diagonal. So NBD, if I want the horizontal, this was 20, this was 15. It's going to be 20 feet over 25 feet, because 25 is my hypotenuse. NBD is going to be minus 6.25 kips. So it's in compression. I'm going to leave it with the negative sign because I'm going to multiply it by my little ends. So I have found now all my big ends, negative 6.25. All I need now are my little ends. So I'm going to pop over to my virtual structure and go from there. So I don't have any external loads applied. So if I sum my forces in X, AX is 0. If I sum my moments about A, BY is 0. So my force is in y, ay is 0. So there's no external reactions, but there is an internal force which could be causing forces on the adjacent members. So I could look at joint A, B, C, or D. So I'd look at A or C, since I know the unit load there. I'll look at joint C to start. So I know I've got this +1 for force AC, and then I've got little n BC and little n CD, and I can sum either one forces in X -1 times 20/25, and CD is -0.8, and sum my forces in Y -MBC -1 15/25, NBC is -0.6. This is -0.6, -0.8. Because my AX and my AY are 0, this looks exactly the same. This is -0.8, -0.6. And if this is -0.8, -0.6, this diagonal also has to be +1. So we could find that if you want to do it out, you could look at joint A and joint B or D, and you will find all those values. But we have all the information that we need to calculate the deflection delta 1. So 1 times delta 1 is the summation of little n big N L over EA. So I've got 2 zero force members. In my real one, I have N AC is 0 and N BC is 0. So I really only need 4 terms here. Let's see, so I've got AC, BC, AB, BD, AD, and DC. Okay, so for this first one, AC and BC are 0. I need AB. So little n AB -0.8 times a +5 times a 20-foot length over EA plus +1 -6.25 times 25 feet over EA -0.6 times 3.75 times 15 feet EA plus my last one DC, which is a -0.8 times a +5, 20 feet over EA. So since I am not plugging in units quite yet, I'm just going to leave it in the current units of feet. So I'm going to leave it as 350 over EA. I'm going to plug it into my compatibility equation and not just calculate a displacement directly. And then I can get F11. I don't have to do any additional work because my redundant applied structure is where I'm going to get F11 from, and that looks exactly like my virtual. So my real and my virtual for F11 look like the virtual for delta 1, which means I can just use those values. I don't have any zero force, so I'm going to have to do all 6 members. So I'll start with AC is a +1 times a +1 times 25 over EA, plus BC is -0.6 times 15 over EA. AB is a -0.8 times 20 over EA, plus BD is the other diagonal, +1, +1, 25 over EA, plus AD is the other vertical, -0.6, -0.6, 15 feet over EA, and the last one, DC, 0.8, it's 20 feet. Alright, so I could have written this a lot faster. I could have written this instead. I could have said +1 squared 25 over EA plus 0.6 squared times 15 over EA plus 0.8 squared times 20 feet over EA, and this whole quantity times 2, since each member there are 2 of that have the exact same. So however you want to write it, if you want to write out exactly for each member, you can. If you want to take shortcuts, by all means, right? The algebra is going to be the same. Do whatever going to make you feel confident in your answer, and we will get F11 is 86.4 over EA. So I've now got delta 1 and F11. Can come back to my compatibility. 0 is minus 350 over EA plus force AC 86.4 over EA. So this is why it doesn't matter if I convert to inches. Both of these would be scaled up by 12. I'd end up getting the same answer. If you want to convert to inches, you can, or you can just leave them like this. And I'm going to get force AC 4.05 kips. I got a positive number. I assumed it was tension based on my redundant applied structure. I assumed that was tension. For FAC, I assumed correctly. So this is in tension. Alright, once I have that, I can now go back to my original structure where I don't have it cut. I've got my 5 kips on there. I've got my reactions. And I now have this member. It is 4.05. And now I can use equilibrium to find remaining forces. So this is going to be method of joints. So I would start with either A or C, since that's where we have the most information. So I look at joint A. I've got the 4.05 in tension. I've got my support forces, and then I have force AB. So I get force AB is 1.32 kips in tension, and so my forces in Y minus 3.75 plus force AD plus 4.05, 15 over 25. Force AD is 1.76 kips in tension. So this is 1.76. This one is 1.32. Alright, so now I'm missing BD, BC, and CD to do at least 2 more joints. Next joint I'll do will be joint C. This is 5 kips. This is 4.05 kips. Force BC, force CD. So my force is next. 5 kips minus force CD minus 4.05, 20 over 25. CD is equal to 2.20 kips in tension. 2.2 kips tension. This is minus 2.76 kips. Only thing I have left is force BD. So I could do joint B or D. I'll just go with D. So I've got 1.76 kips, 2.20 kips, and force BD. And so my force is in X, 2.2 plus force BD times 20 over 25. Force BD is going to be 1.65 kips in compression. So this one is minus 1.65 kips. So I've now found all the internal forces. The big step was I had to take out a member, put it back in as a unit of force in that member. Once I found that, I could calculate the rest of them using method of joints.